Hello everyone, welcome to the fifth lecture of AAE 301. In today's lecture, we will talk about the Fourier series consisting of cosine and sines. Now let's recall what we have learned from the previous lecture first. In the previous lecture, we have looked at a set of exponential functions, and we have seen that that set of exponential functions is actually an orthonormal basis for the Lebesgue space. That means any function f in the Lebesgue space can be expressed as a unique linear combination of the exponential functions in the set. And in today's lecture, we will be looking at another orthogonal set of vectors in the Lebesgue space. And this orthogonal set of vectors is also a non-zero orthogonal basis for the Lebesgue space. So that means that any function f in the Lebesgue space can be expressed as a unique linear combination of the vectors in the set. Now, let's take a look at what that set is. This set is a set consisting of cosines and sines. And also, I've asked you to show that this set of vectors is an orthogonal set of vectors in the Lebesgue space. It turns out that this set of vectors is also a non-zero orthogonal basis for the Lebesgue space. And that means any function f in the Lebesgue space can be expressed as a unique linear combination of sine and cosine functions in the following form. Here we have f of t equals to a naught plus the summation of alpha k times cosine of k omega naught t plus beta k times sine of k omega naught t. And k is from 1 to infinity. And here the Fourier coefficients a naught, alpha k, and beta k, where k is from 1 all the way to infinity, are given by the following three equations. First, a naught is going to be the inner product of f of t and 1, and that's equal to 1 over tau times the integration of f of t from 0 to tau with respect to t. And alpha k will be the inner product of f of t and cosine of k omega naught t, and beta k will be the inner product of f of t and sine of k omega naught t. And if you follow the definition of the inner product, in the end, you will get alpha k equals to 2 over tau times the integration of f of t times cosine of k omega naught t from 0 to tau with respect to t. As for beta k, it will be equal to 2 over tau times the integration of f of t times sine of k omega t from 0 to tau with respect to t. Now, under the spaces, the Parseval's inequality will be given as follows. So here we have the total power of f equals to the squared norm of its sine and cosine Fourier series representation. And now, if you follow the definition of the inner product, you can obtain the following expression that says the total power of f equals to the square of the absolute value of a naught times the squared norm of 1 plus the summation of the squared of the absolute value of alpha k times the square norm of cosine of k omega naught t plus the square of the absolute value of beta k times the square norm of sine of k omega naught t. And here, the squared norm of 1 is going to be 1, and the squared norm of cosine of k omega naught t is equal to 1/2. And also the square norm of sine of k omega naught t is also equal to 1/2. So that's why in the end, we will have the total power of f equals to the square of the absolute value of a naught plus 1/2 times the summation of the square of the absolute value of alpha k plus the square of the absolute value of beta k, and k is from 1 to infinity. Now we have learned two bases for the Lebesgue space, and let's see how these two bases are related to each other. The first basis is a set of exponential functions. And the Fourier series representation for any function f in the Lebesgue space is using this basis is given here. So f of t is equal to the summation of ak times e to the negative I k omega naught t, and k is from negative infinity to infinity. The second basis is a set of cosines and sines. And the Fourier series representation for any function f in the Lebesgue space using this basis is given by f of t equals to a naught plus the summation of alpha k times cosine of k omega naught t plus beta k times sine of k omega naught t, and k is from 1 to infinity. Now let's see how these two Fourier series representations are related. We will start with the Fourier series representation. F of t equals to the summation of ak times e to the negative ik omega naught t, and k is from negative infinity to infinity. So this summation here can be broken down into three parts: the summation of negative k's and a naught, and the summation of positive k's. And here we will move the term associated with a naught to the front. So here, and you see that this e to the negative I 0 omega naught t is actually just 1. So here we are left with a naught. And for the summation associated with negative k's, we will do a change of variable. So basically, we will flip the sign of the k here so that the summation will be from 1 to positive infinity. So here, basically, we just flip the sign of the k, and we will get the summation of a negative k times e to the negative I times negative k omega naught t, and k will be from 1 to infinity. And for the last summation that is associated with the positive k, we doesn't do anything to it. We just move it down to here. And now that now that these two summations are all about positive k's, we can combine these two terms together, and we see that here we have a negative k times e to the I k omega naught t plus ak times e to the negative I k omega naught t. And next, we are going to expand this exponential functions using the Euler's formula. So e to the I k omega naught t will become cosine of k omega naught t plus I sine of k omega naught t. And e to the negative I k omega naught t will become cosine of k omega naught t minus I sine of k omega naught t. And now we will expand these products, and we will combine the coefficients associated with the function cosine of k omega naught t. And we will do the same for sine of k omega naught t. So the coefficient for cosine of k omega naught t in the end will be a negative k plus ak. And the coefficient for sine of k omega naught t will be I times a negative k minus ak. So by comparing the coefficients, we see that a negative k plus ak is actually equal to alpha k, and I times a negative k minus ak is actually beta k. Now we see how these two representations are related to each other. From the previous discussion, we know alpha k is equal to a negative k plus ak, and beta k is equal to I times a negative k minus ak. And this also implies that ak is going to equal to alpha k plus I beta k over 2. And a negative k is equal to alpha k minus I beta k over 2. Now, if the function f is a real function, we know ak is equal to the complex conjugate of a negative k. And if you substitute this equality back into the expression for alpha k and beta k, you will see that alpha k will be 2 times the real part of ak, and beta k will equal to 2 times the imaginary part of ak. Now let's have an exercise to practice what we have learned so far. Here, we will be looking at a function f of t in the Lebesgue space L squared from 0 to 2. And this function is given by 4 plus 2 cosine of 2 pi t plus 4 sine of 2 pi t minus 4 cosine of 4 pi t plus 2 sine of 4 pi t plus 6 cosine of 5 pi t minus 8 cosine of 6 pi t. And because this function is in the Lebesgue space 0 to 2, we know that the period of this function tau is equal to 2. And this also implies that the fundamental angular frequency omega naught for this function will be 2 pi over tau, which is pi in this case. And the sine and cosine Fourier series representation for this function will be equal to a naught plus summation of alpha k times cosine of k pi t plus beta sine of k pi t. And k is from 1 to infinity. And the reason why we have pi here is because omega naught is equal to pi in this case. And now if you look carefully enough, you will see that the original expression of this function is already in the sine and cosine Fourier series representation. So that means the Fourier coefficients a naught, alpha k, and beta k can be obtained by simply comparing the coefficients. And now let's do that. So first, we see that the constant 4 here will be the value of a naught. So here we have a naught equals to 4. And then here we have 2 times cosine 2 pi t. So that means when k equals to 2, alpha 2 is equal to 2. And here we have 4 sine 2 pi t. That means that when k equals to 2, beta 2 is equal to 4. And you can do the same for the rest of the coefficients, and you will see that in the end, alpha 4 is equal to -4, beta 4 is equal to 2, alpha 5 is equal to 6, beta 5 is equal to 0, and alpha 6 is equal to -8, beta 6 is equal to 0. And for the rest of the coefficients, alpha k and beta k, their values are all 0. Now with these coefficients, the total power of the function can be computed using the Parseval's equality. And recall that the Parseval's equality told us that the total power of f will equal to the square of the absolute value of a naught plus 1/2 times the summation of the square of the absolute value of alpha k plus the square of the absolute value of beta k. And k is from 1 to infinity. And we know the values of each of these coefficients. So now we just substitute those values into this expression. And in the end, you will see that the total power of this function f is equal to 86. And that means the norm of this function f is equal to the square root of 86. Now the main part. Let's convert the Fourier coefficients associated with the sine and cosine Fourier series representation into the Fourier coefficients associated with the exponential functions. So here, let's recall that alpha k. First, let's recall that alpha k. First, let's recall that ak is equal to alpha k plus I beta k over 2, and a negative k is equal to alpha k minus I beta k over 2. And we also know that the values of each alpha k and beta k are shown here. Now let's start the conversion process. Let's start with A2. So A2 will equal to alpha 2 let's start with a2. So according to the equation above, we know that a2 will equal to alpha 2 plus I beta 2 over 2. And so that's 2 plus 4i over 2, which equals to 1 plus 2i. Now let's look at another example, a4. So a4 will equal to alpha 4 plus I beta 4 over 2. And that's equal to negative 4 plus 2i over 2, which equals to negative 2 plus I. And you can do the same for the rest of the coefficients, and you will see a5 will equal to 3, and a6 will equal to negative 4i. And for the rest of the coefficients ak, their values will be 0. And because we know that the function f that we're looking at right now is a real function, this implies that a negative k will equal to the complex conjugate of ak. So we can directly compute the value of a negative k by taking the complex conjugate of ak. So here, a negative 2 will be the complex conjugate of a2, and that's going to equal to the complex conjugate of 1 plus 2i, which equals to 1 minus 2i. Similarly, for a negative 4, we will look at the complex conjugate of a4, and that's equal to negative 2 minus I. And you can do the same for the rest of the coefficients. And in the end, you will see that a negative 5 is equal to 3, and a negative 6 is equal to 4i, and a negative k, and the rest of the coefficients, a negative k, will equal to 0. Now with the Fourier coefficients associated with the set of exponential functions, we can plot the power spectrum for the function f. Now recall the power spectrum will be a graph of the square of the absolute value of ak versus the integer index k. And here I have drawn out the power spectrum for this function, and you can see that the sinusoidal components associated with the angular frequency 0, 6 pi, and negative 6 pi have the highest power. And now you may be wondering about why we care about this set of vectors consisting of cosines and sines. And to explain this, we will have to look at two types of functions first, the even functions and the odd functions. So first, let's consider a function f on the real line. And we say this function f is an even function if f of t is equal to f of negative t. Essentially, this means that the function f is symmetric along the vertical axis. And an example for this will be the function cosine of t. Here I have prepared a plot of cosine of t, and you can see that the function cosine of t is symmetric along the vertical axis. So this means that cosine of t is an even function. And this is also true for the functions cosine of k omega naught t for any k that is greater than or equal to 1. And we say a function f is an odd function if f of t is equal to negative f of negative t. So this implies that f of t is skew symmetric along the vertical axis. And one example is the function sine of t. The red line here is the function sine of t, and the green line here is the function sine of negative t. And you can see that if you flip the sign of sine of negative t, then it will be equal to sine of t. This means that sine of t is skew symmetric, and sine of t is an odd function. And this is also true for the functions sine of k omega naught t, for any k that is greater than or equal to 1. Now, it turns out that every function f of t on the real line can be expressed as the sum of an even function and an odd function. So here we have f of t equals to an even function plus an odd function. And that even function is given by f of t plus f of negative t over 2. And the odd function is given by f of t minus f of negative t over 2. And you can verify yourself that this function here is an even function. And you can also verify yourself that this function here is an odd function. Now, if you have a function in the Lebesgue space, then this function is only defined on the interval from 0 to tau, but it can be extended to a periodic function with period tau defined on the real line. So for example, here we have a function f of t in the Lebesgue space, and you can see that this function is only defined on the interval from 0 to tau. And we can extend this function to a periodic function by making copies of this function. So here we have one copy, and here we have another copy. And you can keep on doing this for the entire real line. And in the end, you will obtain a periodic function with the period tau. And as you can imagine, we can now express the even part of the function f of t as a linear combination of the even functions cosine of k omega naught t. Similarly, the odd part of the function f can also be expressed as a linear combination of the odd functions sine of k omega naught t. Now, when you combine the even part and the odd part together, you will see that what we'll end up with is actually the sine and cosine Fourier series representation for the function f in the Lebesgue space. And here comes the most important part. The reason that we look at this set of vectors consisting of cosine and sine is that if the function f is an even function, then we know that this function will equal to its even part and its odd part will be 0. So this implies that the coefficients associated with the odd functions, essentially the beta k's, will be 0 for all k greater than or equal to 1. Similarly, if we know that the function f is odd, then we know that f of t will equals to its odd part and its even part will equal to 0, which implies that a naught is 0 and alpha k will be 0 as well for all k greater than or equal to 1. Basically, the idea is that if you already know whether this function is an even function or an odd function, then expressing this function in terms of a linear combination of cosine functions or sine functions will be more straightforward and simple. Okay, it's time for another example. Let's look at an even square wave and how we can find the sine and cosine Fourier series representation for this square wave. So first of all, the square wave function is given by this expression here. So we have the value of the function equals to 1 when t is in between 0 and delta, and the value equals to 0 when t is in between delta and 2 pi minus delta, and the value equals to 1 when t is in between 2 pi minus delta and 2 pi. And if you draw this function on a plot, you will see that it looks like this. So the function value is equal to 1 when t is in between 0 and delta, and the function value is equal to 0 when t is in between delta and 2 pi minus delta, and the function value is equal to 1 when t is in between 2 pi minus delta and 2 pi. Now this function is in the Lebesgue space 0 to 2 pi, and this implies that the period of the function is 2 pi, and the fundamental angular frequency omega naught is equal to 1. Now we are going to extend the function f of t on the real line. Essentially, we are going to make copies of the original function and then either delay the copies or advance the copies so that the function f of t is defined on the real line as a periodic function with a period tau equals to 2 pi. And you can see from the graph that f of t is symmetric along the vertical axis, and this implies that the function is an even function. Now for this even function, we know that its odd part is 0, so the coefficients beta k will equal to 0 for any k that is greater than or equal to 1. So its Fourier series representation is going to be equal to a naught plus the summation of alpha k times cosine of k omega naught t, and k is from 1 to infinity. And here we know omega naught is equal to 1, so we are left with kt in the argument of cosine. And now let's find out the Fourier coefficients, a naught and alpha k. So a naught is equal to the inner product of f of t and 1. And you can follow the definition of the inner product, and you will see that it's equal to 1 over tau times the integration of f of t from 0 to tau with respect to t. And if you work out this integration, in the end, you will get delta over pi. Now let's look at alpha k. And alpha k is equal to the inner product of f of t and cosine of k omega naught t. And again, according to the definition of the inner product, this will equal to 2 over tau times the integration of f of t times cosine of k omega naught t from 0 to tau with respect to t. And if you work out this integration, you'll see that in the end, it equals to 2 times sine of k delta over k pi. Now we have found the coefficients and we substitute them back into the expression, and we will get f of t equals to delta over pi plus the summation of 2 times sine of k delta over k pi times cosine of kt, and k is from 1 to infinity. And similar to the previous example, let's draw the power spectrum for the function first. And just as a reminder, the power spectrum will be the graph that shows the square of the absolute value of AK versus K. So in order to plot the power spectrum for the function, we will have to determine the Fourier coefficients AK. Here we know the coefficient A naught, and it is equal to delta over pi, but we don't know the rest of the coefficients ak and a negative k for k's that are greater than or equal to 1. So we would have to do a conversion to convert the Fourier coefficients alpha k and beta k into the coefficients ak and a negative k. And to do that, we would have to revert to this equation here. So ak is equal to alpha k plus I beta k over 2. And we know that beta k is 0 for all k that are greater than or equal to 1. So here we will be left with alpha k over 2. And we know alpha k is just 2 times sine of k delta over k pi. So in the end, we know that ak is equal to sine of k delta over k pi. And we know that the function f is real. This implies that a negative k is equal to the complex conjugate of ak. And that's going to be sine of k delta over k pi as well. And you can see that in this case, the square root of the absolute value of ak will equal to the square root of the absolute value of a negative k for any k that is greater than or equal to 1. And this implies that the power spectrum for real function is going to be symmetric along the vertical axis. Here I have plotted the power spectrum of f for delta equals to pi over 2. And as you can see, indeed, the power spectrum is symmetric along the vertical axis for this real function f. And also you can see that the value of the square of the absolute value of ak decreases very fast as k increases. And this implies that the sinusoidal components of f at higher angular frequency have much lower power than those at lower angular frequencies. Now that we have obtained the Fourier series representation for the function, let's look at the Fourier series approximation for the function. So the Fourier series approximation for this function is given by P and T, and it's equal to A naught plus the summation of alpha k times cosine of k omega naught t, and k is from 1 to n. And now we substitute the values of the coefficients into this expression, and we will get P and T equals to delta over pi plus summation of 2 times sine of k delta over k pi times cosine of kt, and k is from 1 to n. And here n essentially will determine how well the approximation is. So here I have a plot that shows the original function f and its approximation when delta is equal to pi over 2. So the blue line here is the original function, and the orange line here is the approximation P1, and the yellow line here is the approximation P10, and the purple line here is the approximation P100. So you can see P1 is a pretty bad approximation of the original function. And as we increase the value of n from 1 to 10, we see that this approximation gets better, but still it's far from perfect. And as we increase the value of n from 10 to 100, we will get an even better approximation. And we see that this approximation fits the original function pretty well in general. But at each discontinuous point, there will be a spike. And in the literature, this is called the Gibbs phenomenon. So essentially, this happens because we are trying to approximate a discontinuous function with a continuous function. And if you want to know more about this phenomenon, you are welcome to refer to page 23 of the slide. Also, there's one thing that I would like to point out from this graph. By observing the components in this graph, we see that the sinusoidal components of f at higher angular frequency indeed have much lower amplitudes. And this is result from the fact that the square root of the absolute value of ak is low when k is large. Now let's look at how we can compute the approximation error. Here we have the Fourier series representation for the original function f and its Fourier series approximation, P and T. And now let's look at the total power of the approximation error. So first, this expression on the right can be obtained by substituting the two expressions above into this expression on the left. And what you end up with will be a summation of alpha k times cosine of k omega naught t, and k is from n plus 1 all the way to infinity. And according to Parseval's equality, this will equal to 1/2 times the summation of the square root of the absolute value of alpha k, and k is from n plus 1 to infinity. And this result here can also be seen as the total power of f subtracted by the total power of its approximation. So here, the total power of f is going to be the inner product of f. And after some computation, you will see that this will equal to delta over pi. As for the total power of the approximation, we can again apply the Parseval equality, and you will see that it's going to equal to the square root of the absolute value of delta over pi plus 1/2 times the summation of the square root of the absolute value of 2 times sine of k delta over k pi, and k is from 1 to n. And in the end, we will see that the total power of the approximation error is equal to delta over pi minus delta squared over pi squared minus 2 times the summation of the square of sine of k delta over the square of k times the square of pi, and k is from 1 to n. And for the example that we have seen above, the total power of the approximation error between f and p100 will be around 0.0010 when delta is equal to pi over 2. So that implies that the approximation error between f and p100 will be around 0.0318. And if you want to know more about how to compute the approximation error, you are welcome to refer to page 37 of the slide. Great. This is the end of today's lecture, and I hope to see you in the next one.